Hello, I'm Sheldon Axler, the author of Linear Algebra Done Right. This video discusses part 1 of the section of the book titled Characteristic and Minimal Polynomials. In this video, we will focus on the characteristic polynomial. Let's quickly review our standard assumptions. F denotes either the scalar field of real numbers R or the scalar field of complex numbers C. V denotes a finite-dimensional, non-zero vector space over F. We are now ready to define the characteristic polynomial. Suppose V is a complex vector space and T is an operator on V. Let lambda 1 up through lambda m denote the distinct eigenvalues of T, with multiplicities d1 up through dm. Then the polynomial displayed here is called the characteristic polynomial of T. Let's look at an example. Suppose T is the operator on C3 defined by the equation shown here. With respect to the standard basis of C3, here's the matrix of T. As you can see, this is an upper triangular matrix. Thus, the eigenvalues of T are the numbers along the diagonal, and those are 6 and 7, and we can also see the multiplicities of these eigenvalues from the number of times they appear on the diagonal. So 6 has multiplicity 2, and the eigenvalue 7 has multiplicity 1. Thus, using the definition of the characteristic polynomial, we see that the characteristic polynomial of T is a polynomial z minus 6 squared times z minus 7. Note that this definition of characteristic polynomial only applies for complex vector spaces. On real vector spaces, we have operators that have no eigenvalues. Thus, we need another definition of the characteristic polynomial for real vector spaces. We will get to that in a future video. Let's wipe away this example so we have room to display some easy consequences of the definition. Suppose V is a complex vector space and T is an operator on V. Our first consequence of the definition is that the degree of the characteristic polynomial of T is equal to the dimension of V. This follows easily from the definition to the left because we have a result stating that the sum of the multiplicities of all the eigenvalues of T is equal to the dimension of V. Thus, this result follows immediately. Our second consequence of the definition is that the zeros of the characteristic polynomial of T are precisely the eigenvalues of T. Again, this follows immediately from the definition to the left. Many treatments of linear algebra give a definition of the characteristic polynomial using determinants. As we will see in a later video, that definition turns out to be equivalent to the definition given here. However, the definition given here has several advantages. The approach using determinants uses the characteristic polynomial to show that eigenvalues exist and that the sum of the multiplicities is the right thing. However, we've proved that without using determinants at all. Thus, our definition makes sense, and it's more closely connected with what's going on in terms of the operator. We're not losing anything computationally because determinants are a wildly inefficient way to compute eigenvalues. Lots of textbooks are filled with toy examples of 2x2 and 3x3 matrices and using determinants to compute eigenvalues of those matrices. However, in the real world, matrices tend to be much bigger, and nobody uses determinants for finding eigenvalues of those larger matrices. The major result about the characteristic polynomial is the Cayley-Hamilton Theorem. It says that if V is a complex vector space and T is an operator on V, and Q denotes the characteristic polynomial of T, then Q applied to T is equal to the zero operator. As we'll see, the proof of the Cayley-Hamilton theorem using the approach used here is quite instructive. Let's look at that proof. Let lambda 1 up to lambda m be the distinct eigenvalues of T. Let d1 up to dm be the dimensions of the corresponding generalized eigenspaces. In other words, d1 up through dm are the multiplicities of these eigenvalues. Each t minus lambda ji restricted to the corresponding generalized eigenspace is nilpotent. That means if we raise it to a large power, we get 0. We know from previous results that we need to raise it only to the power of the dimension of the space, which is dj. Thus we have the last equation shown here. Now every vector in V is a sum of generalized eigenvectors. That result follows from our decomposition theorem. Thus, to prove that Qt is the zero operator, we only need to show that Q of t restricted to each generalized eigenspace is the zero operator. Thus, let's fix a j, so we can do that. And we have, by definition, Q of t is equal to the polynomial displayed here. Remember, Q is the characteristic polynomial of t. The operators on the right side of the equation above all commute with each other. So we can move the factor t minus lambda ji to the power d sub j to the last term in the expression on the right. And now, when we apply it to the space of generalized eigenvectors corresponding to lambda j, we get 0. Look at the last equation in the first column. In other words, we've proved that the operator q applied to t restricted to the generalized eigenspace lambda sub j of t is equal to 0, and thus Q of t is a zero operator, completing the proof of the Cayley-Hamilton theorem. This concludes part 1 of the video on characteristic and minimal polynomials. If you see a small picture of a slide in the upper left corner of this slide, then you can click on it to get to the next video. If you see a small picture of part of the cover of Linear Algebra Done Right in the upper right corner of this slide, then you can click on it to get to the book's website.